Good morning. Here we are yet again for another lovely session of CENG 4412 Steel and Concrete Design. This is the 20th lecture in the video series, and today we're going to finish up looking at short concrete columns by discussing a column moment interaction, or moment interaction diagrams. So let's look at interaction diagrams. As we discussed previously, in almost all cases, columns are going to experience, or concrete columns are going to experience some level of moment. And this is really because of their sort of monolithic construction. When I say monolithic, I mean two things. One, I mean they have larger dimensions, which means you're more likely to get eccentric loadings, and also they are cast together with their beams in most cases. So because of that, you're going to, or they're locked together with their beams and floor slabs, that sort of thing. And so because of that, it's almost inevitable that your connections are going to transfer some amount of moment to your columns. So now we discussed how short column design takes that into account. And this stuff is all laid out in chapter 10 of the ACI code. But let's look at interaction diagrams. So fundamentally what an interaction diagram is a diagram showing the axial capacity versus moment present in a concrete column. So axial capacity versus moment is shown in a diagram. And essentially what we're going to do is we're going to have some critical points. We'll do some calculations at a few critical points. And this will produce the outer boundaries of our region, of our acceptable region. The outer bounds of an acceptable region. Or acceptable load. So again, as we recall, concrete columns are always going to be experiencing some level of moment in addition to axial capacity. So imagine I were to create a graph of phi Pn and phi Mn for a given concrete column. And let's say I have phi Mn here and phi Pn here. The factored axial moment moment capacity here and the factored axial capacity here. You would end up getting some sort of, if we calculate, so what this basically comes down to is that the more capacity that we're using for axial, the less capacity we have for moment, and vice versa. Because again, we have learned previously that both moment and axial force are carried by axial stress. So the big idea here, more moment or more capacity given to moment equals less capacity for axial loading. And vice versa. Okay, so there's that. Again, so we have a certain amount of capacity, and if it's getting used up in one versus the other, there'll be less available for the other. So here, if we were actually to plot the capacities of this, though, the maximum sort of critical capacities, we end up getting a curve something kind of like this. And so basically we're going to lay out a curve that we look at a few critical, the big idea here is that we're going to look at a few critical points where we're going to consider a few critical points that determine the outer bounds of this curve. And then based upon that, everything in this acceptable region, or everything in the middle of this region, is the acceptable region. So this is the acceptable region. So look at this curve, for example. At this point here, we're right on the phi mn axis. What this represents is what would be the axial capacity of the column at this point. Yeah, or the axial capacity would just be, the axial load capacity would be 0, yes. And so basically here, in the case where we have our maximum moment, we have 0 axial point load capacity. In the case where we have maximum compression, there we have maximum compression or maximum tension, we have 0 moment capacity. And so based on this, we're gonna create a curve. We're going to create a curve based on 4 points for a given section, and this will be the outer bounds of our acceptable region. And then the way you prove a column is you find the actual so you create the basic process for this is that you're going to create for any given short concrete column, you create your curve based on this. You create a curve here. Oh, I'm having some difficulty here. You create a curve, and everything inside that region then is going to be fine. Okay. And that's the basic idea. Okay, so what I want to do is I want to do a long form example demonstrating how we actually solve for this. So let's look at calculating an interaction diagram. I want to work through and find 5 points, and I want to describe a section and then find 5 critical points, and then in turn find, once I have those 5 points, I'll use those to define my interaction diagram. So let's look at calculating an interaction diagram. I'm going to work with the following section. And it's going to be a concrete column. And this will be a short concrete column. So we don't know its exact length, but that's fine for now. All I'm trying to do is calculate the interaction diagram. And let me show you the dimensions. So I'm going to have 4 number 9 bars at the top and 4 number 9 bars at the bottom. So this is going to be 4 number 9 bars and 4 number 9 bars, top and bottom. So no matter which direction this thing bends, I have 4 at the same distance. So I'm going to go with this. This is going to be relatively simple. This is going to be a simplified problem with nice symmetric sections, etc. And so this is going to be, my B is going to be 16 inches, and my H is also going to be 16 inches. And my H is also going to be 16 inches. And then I'm going to have D, the distance from the top of here to the middle of the, to the centroid of the main tension steel. So D here is going to be 13.5 inches. And then D prime, which if you recall, is the distance to the compression reinforcement. D prime here is going to be 2.5 inches. And I'll go ahead and show it, but it's not going to be important to this problem. We would also have some confining reinforcement or some shear reinforcement here, depending on your perspective. Maybe you have one, maybe you have one tie here. And so this is not going to be critical for this problem, but I'll go ahead and show it. So you'd have a number 3 bar, number 4 bar, probably a number 3 bar, snaking its way around. And ideally, it would be better constructed than it is drawn here. It's a very Christmas-looking concrete section. Let's see, what else do we need to know? Well, it would be nice to know the properties of this stuff, or the material properties. And the relevant material properties are going to be Fy and F prime C. Fy is going to be 60 KSI, is going to be 60 KSI, and F prime C is going to be 5,000 PSI. And F prime C is going to be 5,000 PSI. All right. And so really that's all we need to know. We have all of our, we have our cross section, we have our concrete stress, we have our steel stress. That should be everything we need in order to calculate our column interaction diagram. Okay. So basically I'm going to have 5 critical points that I'm going to use to define this column interaction diagram. And so I want to run through and work through a series of calculations, finding the stress of each, or finding the loads at each of these points. So the first point, oh, actually maybe I can give you a little rundown here. This is sort of my roadmap. My roadmap here. I'm going to have really 5 critical points. I'm going to call these 1, 2, 3, 4, and 5. Makes sense. 1, 2, 3, 4, and 5. 1 will be the max compression, or so the maximum compression case. This would be where there is basically no moment applied, and this is a pure compression failure. 2 would be my max tension capacity. In other words, I'm just going to pull on this concrete as hard as I can, and really the only thing resisting it is going to be the tension in the steel. And the actual curve looks something like this at the end, but preferably better drawn. And then the third case, number 3, this is going to be the balanced failure. The balanced failure is going to be the case where you have the maximum moment, because everything is the force in the axial and the force in the concrete and the steel are nice and balanced, and so that's where you end up with your maximum, most efficient bending moment capacity. So then we have the balanced failure. 4 is going to be the, let's see, we have here, the case where the epsilon steel 1, the strain in the first layer of steel is going to be 0, or the basically this is the tensile steel has 0 strain. Or tension steel has 0 strain, and case 5 will be where epsilon S2 is 0. This is where the compression steel has 0 strain. Compression steel has 0 strain. Here. Let's see here. Actually, that's not quite right, sorry. Not compression steel has 0 strain. That's a little bit wrong. Sorry about that. I'm not going for symmetry here. This is the tension controlling limit strain case. Tension controlled limiting strain case. Limiting strain case. Okay. So here, let's consider this. Let's see. So, let me check something really quick. Just make sure I'm on the right page. Yes. Okay. All right, moving on. Let's start with this. So I'm going to calculate the first one. This is the case where we have max compression. Compute max compression. And so here, In the max compression case, you have no bending. So basically, the concrete is being loaded up to the maximum of its limit, and so the concrete's being loaded to its maximum compressive capacity, and all of the steel in the cross section is also being loaded to its maximum its maximum compressive capacity. So here, and we can just base this off the gross cross sectional area for simplicity. Although, sort of, we got to be a little bit more careful with this. Well, no, that'll work. So, first let's get the gross area. This is going to be 16 times 16 inches times 16 inches, which will equal 256 inches squared. And we know number 9 bars each have a cross-sectional area of 1 square inch. So the area of steel, AST, is just going to be 8 inches, or 8 times 1 inch squared. Or just 8 inches squared steel area. And then I want to get the ASFY. That's would be no, number 9 bars have an area of 1 inch squared, unless I'm really.
Yeah, area 1 squared.
That's diameter, not area. Yes, making me question my sanity this morning. Thank you. It's not a very difficult thing to do, mind you. So the ASFY is going to be 8 inches squared times the yield stress. So 8 inches squared times the yield stress of 60 KSI. And this will come to 480 kips. So that's the steel compressive capacity. And for the concrete, capacity, we can just use our old 0.85 F prime C, 0.85 F prime C times the area of the concrete. And this is then going to equal here 256 here. Well, actually not quite. Here, we have to make a slight adjustment to the area of the concrete. Now, we could possibly neglect this difference, but if I'm going to do this right and proper, I probably should. So the area of the concrete is not exactly 256 square inches. This is going to be 0.85. F prime C would be the 5 KSI, but the actual area of the concrete is going to be the gross cross-sectional area. So here's your gross cross-sectional area, and then you have your steel inside. So if I really want to calculate the area of the concrete precisely, I need to subtract the area of the steel from the area of the concrete. It's a very small percentage of the overall area. It's probably not going to have, if your column is so tightly designed that it's depending on that not to fail well, you're probably being too probably not being conservative enough. But oh well, if we're going to do this, let's do it right and proper. So the area of the concrete will be 256 minus 8, and if you plug and chug on that, you will find that this produces a capacity of 1,054 kips. Concrete capacity. So the overall P naught, or P1 here, so for the P for 0.1 is going to be then simply the sum of these. It's going to be the P of the steel plus the P of the concrete. So 480 kips plus 1,054 kips. And this comes to a total capacity of 1,534 kips, if I can talk properly. 1,534 kips. And here, this is the max compression case. So at max compression case, essentially the Mn is 0. So we now have a location on our curve here that corresponds to 1,534, comma 0. So that will be our 0.1. So our P, comma M is going to be 1534, comma 0. For our, and what we're working on so far is going to be Pn and Mn. I'm going to calculate the initial capacities first, and then later we can go back and calculate, sorry, I'm going to calculate the nominal capacities first, and then later we can come back and calculate the factored capacities, or the design capacities. Okay, so next I want to work on the axial tension capacity, the max tension case, to compute axial tension capacity. And I would like to give a brief note on this, on signs. So here, you notice that the case 2 is going to be the max tensile capacity. Now, this may seem a bit strange at first. What you may notice at first, that tension here is negative, and that may seem a bit strange because if you're familiar with most cases of structural engineering, generally we use positive for tension and negative for compression. But just by sign convention, we usually put this because this is for columns. These interaction diagrams are for columns. Generally, we put compression as positive on these things. So max tension capacity, and so here we are going to neglect in the max tension case, as we always kind of do. We neglect tension in the concrete. We neglect the tension in the concrete. So we're going to neglect the tension in the concrete, and so the only tensile capacity comes from the steel. The only tensile capacity is from the steel. And so then I want to find the axial load, and here again, also in this case, we will also have no flexural load, or no moment. So here, the P for this point is going to be negative ASFY. Negative ASFY, so we're using the same calculation from before, except we're putting a negative on it because it's going to be in tension rather than compression. So that's going to be negative 8 inches squared times 60 KSI, and that's just negative 480 kips. So this will then produce a point on the diagram, again with a 0 moment, and this is going to be negative 480, 0. So our PN MN for point 2 is going to be negative 480, 0. All right, any questions so far? So far I've only been looking at axial loading, so things have been relatively straightforward. But what I'm going to be doing going forward is just going to be working with the other cases, and these are going to involve some flexure as well as axial capacity. Okay, next I want to look at case 3, the complete balanced failure. So here, the balanced failure case, and if you remember from our discussions of moment capacity, a balanced failure means that we have a few things. One, we're going to have the strain in the concrete is equal to our 0.003 crushing strain value, and the strain in the lower steel, epsilon S1, the bottom steel, the tension steel basically, is going to be equal to the yield strain of steel. So epsilon yield basically. So let's look at this from a stress and strain property. So or from a stress and strain perspective. So first I want to look at this in terms of strain. So I'm going to look at this first in terms of strain and then in terms of stress. First for strain, then for stress. And here,
Chandler, is it in the code that we can?
interaction diagrams really aren't described explicitly in the code. I mean, it tells you, they are mentioned in the commentary in chapter 10, but you're not going to find a step-by-step detailed procedure for calculating them. There are some ACI calculated ones that you can reference, but you're not going to find a detailed step-by-step procedure to calculate the interaction. Instead, what it says, if you read the code, what it says is structural engineers should consider interaction, and so you're required to consider interaction, but it's not going to tell you how to do that, just like it's not going to tell you how to calculate the moment of inertia of something. Except for the more complex cases of like effective moment of inertia or something like that. But yeah, unfortunately, this is not spelled out directly in the code. So here, the strain, assuming everything is nice and linear, is going to be like this. At the bottom, we'll have epsilon S1, and that's going to be our yield strain. Then at the top, we'll have 0.003. And then here, below the maximum compression strain, we'll have some epsilon S2, and that is this is the strain in the compression steel. This is the strain in the compression steel. Okay, so we'll have that. And then we also need to remember our definition for C, that is our distance from the top to the neutral axis, or Christmas diagrams. And then I want to look at this from the point of view of stresses and forces, or at least I should say stresses. Here, I'm going to have an FS1 and an FS2. So I have an equivalent, so I have some, my tension steel will be at some FS1, and then I'll have some FS2 at epsilon, at the location of the compression steel. FS2 is the stress in the compression steel. Then I'm going to have some compressive stress in the concrete at a depth of A, and this is going to be the 0.85 F prime C. .85 F prime C, and this is at a depth of A. And this is just very similar from what we've looked at previously in terms of beam moment capacity. This is depth A, the depth of our Whitney stress block. And then as the result of these stresses, we will get some forces. And the forces are what we're going to use to actually calculate our moment capacity. So from the stresses, I'm going to find equivalent forces. So I'll have some capital F1, some capital FS1. This would be the force in the tension steel. I'll have some capital FS2, and this is going to be the force in the compression steel. And then I'll have something that I'll call C sub C, the compression capacity of the concrete. And all of this stuff must come together to form my PN and my MN. My strains will lead to stresses, and those stresses will produce forces, and those forces will produce the ultimate axial capacity and moment capacity of the section. So basically the approach of this is I am looking at the section. When I'm calculating this interaction diagram, I'm basically picking a few key points, usually in terms of strains, critical strains and things like that, critical stresses, whatever we want to call it, or depending on the condition, or depending on the point. And then based upon that, I'm saying, okay, well, if strain is at this, what kind of stresses do we get? And if the stresses are like this, what kind of equivalent point forces do we get? And then once we have those equivalent point forces, what are the final axial and what are the resulting axial force and moment that will produce those internal stresses and strains? Okay, so let's run through this. And the rest is just math. Famous last words. So here, first epsilon S1, again, is going to be my yield strain of steel, as I discussed previously. And that's just Fy divided by 29,000. So 60 divided by 29,000 equals 0.00207. 0.00207 here. And next, I want to compute C. I want to compute the distance to the neutral axis. And I'm going to do this using similar triangles. So I know that point 003, I'm going to compare this triangle here to this triangle here. And I also know that the overall D here, the depth here, is 13.5 inches from the top to the bottom. So I know here, if I'm just applying similar triangles, that point 003 divided by C is equal to 0.00207 divided by 13.5 minus C. Just applying similar triangles. And here I find that C is equal to 7.99 inches approximately. So almost right near the middle of the section. And really for a balanced failure, that's not a bad location for that to be. And so then once I have that, I can apply similar triangles again. Once I know that this C is 7. So again, to find C for this case, I apply a similar triangle comparing this triangle to this triangle. And then once I have that, I can apply a second similar triangle comparing this triangle here to this triangle here. It's just triangles, triangles, triangles all the way down. So epsilon, I can again use similar triangles. Epsilon S2 over 7.99 minus 2.5. Where did that come from? Again, I'm using this as my smaller triangle. And if it's 2.5 from here to here, and it's 7.99 from here to here, the depth from here, or the height from here to here is 7.99 minus 2.5. And this is then going to compare to 0.003 divided by 7.99. You work through the math on that, and you will find that epsilon S2 is going to be equal to 0.00206. 0.00206. So I have my strains, and then and next I'm going to go and find my stresses accordingly. So we know all of our strains. We know the maximum strain in the concrete, as of course our O is always going to be our 0.003. I know the strain in my upper steel, my lower steel, my epsilon S1 is going to be 0.0027 or 0.00207. And my epsilon S2, my strain in my compression steel, is going to be 0.00206. So now you can see why this is referred to as the balanced failure. If you notice, the strain in both of these is very similar. Next, I want to find stresses of these things. So FS1, the stress here, is just going to be epsilon S1, the strain times the modulus of elasticity. Same thing for FS2, epsilon S2 times the modulus of elasticity. So that's going to be 0.00207 times 29,000. And this comes to 60 KSI. And FS2 is going to be 0.00206 times 29,000. And this comes to slightly less at 59.8 KSI. 59.8 KSI. Then here, if I want to get the stress in the concrete, 0.85 F prime C. So that's going to be 0.85 F prime C. So again, the strain, the stress in the concrete, 0.85 times 5, and this is going to be 4.25 KSI. So 0.85 F prime C. So basically, this is the strain. These are the stresses the steels are going to be under, and this is the stress our Whitney stress block is going to be under. Next, I want to calculate the depth of the Whitney stress block. And if you remember from previously, it was beta 1 times C, where beta 1 is a factor. Let me remind us of the citation on this. Beta 1 is a factor from 22.2.2.4.3. And if you see, we do have concrete in the range where we need to slightly adjust beta 1. And if you run through the calculation, you will find that beta 1 in this case is equal to, yes?
I'm sorry, it's 0.805 times what?
F prime C.
0.85 times F prime C.
I know, the next.
Times 5.
Times 5, yes, 5 KSI.
5.
Mm-hmm. Thank you. So 0.8 times, so again, running through the beta calculation here, that basically the interpolation that we've discussed previously, the beta 1 there is just going to be, when we run through that calculation, you'll find that beta 1 is equal to 0.8. And I know I'm moving through this kind of quickly, but there's a lot of ground to cover today. So 0.80 times 7.99 inches, and this will come to 6.39 inches. Again, because beta 1 is equal to 0.80. So we now have the depth of Whitney stress block. We now have the stress in each of the steels. We have the stress in the concrete. So the stress in the steel, the stress in the concrete, and the depth of the Whitney stress block. Now let's get the forces. So the strain in the steel one, FS1, is going to be lowercase s FS1, the stress in that steel, times the area of steel 1, AS1, and this is going to be 60 KSI. So basically, this is my the force in my tension steel, and next I'm going to have the force in my tension steel, and then I want to have the force in my compressive steel, etc. So 60 times 4, 60 KSI times 4 inches squared, and this comes to 240 kips here. Now, FS2, I might be tempted to say, oh, this is the stress here is 59.8. Let me put a negative on there. Or no, let's not put a negative on there. It'll balance out. 59.8 times 4. Is that right? It actually isn't. Any idea why? I would be tempted to say that the actual force produced by my compressive steel, is 59.8 times 4. I'd be tempted to do that. But the concrete, yeah. See, here's the thing. I'm going to calculate the Whitney stress block. And I'm going to use the Whitney stress block, when I calculate the Whitney stress block, I'm going to calculate this, so this is not actually correct. When I calculate the Whitney stress block, or the force from the Whitney stress block, I'm just going to do that as the depth of the Whitney stress block times the width of the cross section. If I do that, though, I'm going to be double dipping, at least in the area of the compression steel. If I'm not careful, I'm going to be double dipping. So I would end up basically counting I would be basically be figuring, oh, I'd be basically saying in my calculation that there's both concrete and steel at the exact same location, and we know that's not possible. So for the compression steel, what I'm going to do is I'm actually going to subtract the stress that I'm going to know. I know the concrete's going to be under. So I'm just going to do a little bit of fudge factor and adjust the stress from 59.8, but I'm going to subtract the 4.25 from this. I'm going to subtract the stress in the concrete. And this will keep me from double dipping, basically, times 4 inches squared. Again, this is the actual stress I would predict in the steel there based on its strain level, but the concrete. But I need to have sort of adjust this so that I am not double dipping. And an alternate way to do this would be to reduce the effective area of the Whitney stress block. But mathematically, it's the same thing no matter what you want to do.
Good question. But if you don't subtract it, you should be more conservative.
If you don't subtract it, you'd actually end up. I believe I have to run through the math, but if you don't subtract it, you're actually not being conservative. You're being the opposite of conservative. You're
It's the concrete.
exactly. You're counting on capacity you don't actually have. So, now I'd be tempted to say you'd be liberal, but I mean, really, that context you never really hear that used much in engineering parlance. It's conservative refers to not making conservative assumptions, but I guess you could use making liberal assumptions, but you don't hear that used very often because it's the context just isn't quite right. Anyway, politics. 222 kips. So this will come to 222 kips, and then the force in the concrete is going to be 0.85. 0.85 F prime C times A times B. So this is 4.25 times 6.39, the depth of our Whitney stress block, times the width of this section, which is 16. And that comes to 434.6 kips. So I now have three forces: the force in the tensile steel, the force in the tension steel, the force in the compression steel, and the actual force in the concrete, the actual net equivalent force. And all I need to do now is apply equilibrium. And once I apply equilibrium, I can actually find the point on this curve. So here, apply equilibrium. So here I'm going to have these three things. So let me just let me put together a little diagram just as a reminder. I'm going to have the C sub C. C sub C is at a distance, and the depth down here is going to be at a distance of what? Well, it's going to be A over 2. A over 2 there, if we math that correctly. And then also what else? We have, so that's going to be A over 2. Then we'll have the, we'll also have the FS2, which will be at a distance from the top of what? That would be of 2.5 inches. That's going to be our D prime. And then we have our FS1 opposing this. And this is at a distance D of 13.5 inches. So this is a side diagram of the forces and distances. So first I'm going to do a sum of forces in the x direction is 0. And so the sum of forces in the x direction must equal 0. Therefore, the compressive capacity of the concrete plus the compressive force, the equivalent force in the compressive steel, my FS2, minus FS1, must come together to equal the PN, the nominal axial capacity. And so this is 434.6 plus 222 minus 240 equals P sub N, or this equals 417 kips. 417 kips. Now I'm going to take to find the moment capacity, I'm going to do a balance of moments, and I'm going to do them about the centroid of the section. I'm going to do a sum of moments about the centroid. So not about C, but about the centroid of the section. Now for this, they're actually fairly close, but generally we want to take the sum of moments about the centroid. So the sum of moments here is going to equal FS1 times D minus H over 2. H is the overall, so the overall thing here is H, so yes, again here, yes, 16 over 2. So plus FS2 times H over 2 minus D prime plus C sub C times H over 2 minus A over 2. Then putting in numbers, I put in numbers for this. This is 240 times 13.5 minus 16 over 2. 13.5 minus 16 over 2 plus 222 times 16 over 2 minus 2.5 plus 434 times 16 over 2 minus 6.39 over 2. 16 over 2 minus 16, or 6.39 over 2. So it's just plug and chug at this point. And if we work through this, then we get 1320 plus 1222 plus 2088 equals 4,630 kip inches. Or MN, if I convert this to kip feet, so MN then is going to be equal to 4,630 kip inches, or 386 kip feet. So we now have the third point on our diagram, point 3. And this is going to be 386, again, for PN, comma MN, PN, comma MN, This is going to be 386, comma 417. 386, comma 417. Okay. Moving on, next, my next case is going to be where epsilon S1 is equal to 0. So in other words, there is no, I'm going to be looking at the case where the strain in the tension steel is 0. So let's consider the case where basically the strain in the tension steel is 0. So epsilon S1 equals 0. So here, and this one's actually a little bit simpler to calculate, thankfully, mercifully. Not that the other one was too bad. So we have strain, and so essentially I'm assuming here, this would be the case where the neutral axis is actually at the tension steel. So I would have something like this. And this seems odd at first. How would you ever have 0? This may seem odd at first. You might think, how in the world would I ever have 0 strain in the tension steel? And from the point of view of beams, this does seem odd. But when you start remembering when you start recalling that we not only have moment, but we also have axial force here, if you imagine the stress diagram of from normal bending, a sort of a normal stress diagram. From bending, if I then in turn superimpose upon that a large compressive load, the compressive stress will tend to cancel out some of the tension stress, and it will kind of adjust it will shift the curve to the right, basically. But maybe you don't need to worry about that too much. But the key point here is that my epsilon S1 is 0, and then I'll have 0.003 here. And my neutral axis is actually going to be just at D. So this case, my C is going to equal D. Because again, the C is defined as the depth of the neutral axis. So if and the neutral axis, of course, is the location of 0 strain. And so therefore, if the bottom tension steel has no strain in it, then the neutral axis must be located there, and C must equal D. So C equals D, or in our case, 13.5 inches. And then I would still have some strain in the tension steel. And this would be just my epsilon S2. I will need to calculate that. So let's calculate. Let's go ahead and do that. I want to apply similar triangles to calculate epsilon S2, if I can manage to talk properly. And so I'm going to say epsilon S2, so I'm going to compare this triangle to this triangle. Again, the small triangle to the big triangle. Epsilon S2 divided by C is going to be equal to, epsilon S2 over C is going to be equal to 0.005. Oh, sorry, wrong thing here. Derp. Epsilon S2 over 13.5, getting ahead of myself, minus 2.5 is going to be equal to 0.003 divided by 13.5. And if you plug and chug on that, you will find that epsilon S2 is going to be equal to 0.002444. Okay, so now we have the strains everywhere, we can find the stresses. So the stress here, well, the stress is going to be greatly simplified because we don't have to worry about the capital FS2. Instead, we're going to have just a Whitney stress block at some depth A, some depth A of 0.85 F prime C, and then we'll have some FS2. Some FS2 here. And so this would be our stresses. And we're just going to do the same thing we've done before, where we start with strain. Oh, I shouldn't have erased that, but I'll just put that back. We're going to do the same thing we did before, where we have some strains. We'll see what kind of stresses those produce, and then we'll see what kind of point loads, and then we'll balance them, etc., etc. Just like we always do. And here, A is going to equal beta 1 times C. So it's going to be 0.8 times 13.5, and this comes to 10.8 inches. Comes to 10.8 inches, and then the stress is going to be the same as before, 0.85 F prime C is going to come to 4.25, no change there. And the stress in the steel, FS2. Now, interestingly enough here, well, we'll get something kind of interesting here. This is kind of neat. FS2 is, according to certain definitions of neat, FS2 times E. This is going to be 0.002444 times our modulus of elasticity of 29,000, and this comes to 70.9. So I'm finding the stress in the steel, the compression steel, is 70.9 KSI. Do y'all see a problem with that? How can the steel have a stress in it greater than its yield stress? In all of our, now, if we ignore us now, if we speculated on some strain hardening or something, sure. But in all the kind of design we've done this entire semester, we have never used anything greater than the yield stress, so especially in our concrete design. So basically what this is showing is that our stress in our compression steel is going to exceed the yield stress. So instead, we're going to have to limit this and say, okay, this is not actually possible. So we're going to limit this. We can never get more than the yield stress. FS2 is going to be equal to 60 KSI max. So regardless of what the strain would indicate, this thing is going to be limited to the yield stress. Again, if you remember our stress strain diagram or our DLI stress strain diagram for steel, we assume this kind of behavior here, where it goes, where basically it goes up to, you have elastic behavior right up to the yield stress, and then it just yields horizontally from there. That's our standard design assumption for the concrete and steel design. Okay, so next I need to find the equivalent forces. So I want to look at forces. You might say we need to bring balance to the forces. Oh, Star Wars joke. Wow. Okay. Can you tell it's almost Thanksgiving break? Okay. So I'm going to have some capital FS2 and some C sub C. The force in the concrete and the force in the steel. And again, just like I did previously, I'm going to have to subtract. I'm going to have to reduce the stress in the concrete or in the compression steel to keep from double dipping. So FS2 is going to be equal to 60 minus 4.25 times 4, and this comes to 223 kips. And C sub C is 4.25 times 10.8 times 16. 10.8 again was the depth of the Whitney stress block that we found previously. And that comes to 734.4 kips. Then if I apply equilibrium, so if I do a sum of forces, so now we apply equilibrium. If I apply equilibrium, well, I can just say, okay, well, P nominal, the nominal axial capacity is 734.4 plus 223, and that comes to 957.4 kips. 0.4 kips here. And let's see here. Now, the moment capacity then, let's see here. My notes are clipped off a bit here, but nominal moment capacity is going to be 223 times 8 minus 2.5 plus here plus 223 plus 8 times 8 minus 2.5 plus 734.4 times 8 minus, that would be 10.8 over 2. 8 minus 10.8 over 2. So 8 minus 10.8 divided by 2. All right, so that's going to be 8 minus 10.8 over 2 and 8 minus 2.5. Okay, and what that comes to then is a nominal moment capacity that will be the sum of 12, 26.5 plus 1909, and we get 3,136 kip inches or 261 kip feet. So we now have our fourth term, or our fourth point on our diagram, and this is going to be again a Pn, comma Mn, Pn, comma Mn equal to 261 here. Actually, if I've been using PMNN, so that's a little backwards here. Anyway, let's see. Actually, yeah, I believe I've been doing MNPN. I think, actually, you know, this is a typo here. That should be MNPN, yes. Sorry about that. MNPN, and then I do this. Did I do the same thing over here? Okay. Oh, little typos. So, well, I actually want MN. No, because I always put the axial moment or axial capacity on the negative, so it's going to be 0, comma negative 480. Did I not? Yeah, no, so that is correct. See here. I just have this little backwards. So it should be MN, comma PN. Sorry about that. Slight adjustment. 0, comma 1534. If I'm being consistent with my ordered pairs, I should probably adjust those. Okay, so then that will come to 261. Again, I need to put it MN, comma PN. Sorry about that little typo. 261. Can it still be called a typo if you wrote it by hand? Anyway, 957.4. And that's our fourth point. Now we just have one more point to determine. And then we need to figure out how the heck we integrate phi factors into this. So let's do that. And then the fifth case is going to be in a tension-controlled limiting capacity. The tension-controlled limiting capacity now, if you remember our discussion of previous phi factors, the tension controlled was defined as any time the strain in the steel was over 0.005. So we're going to use that as our limiting, or basically, we're going to assume that and then calculate everything based on that. In other words, we're going to assume in this case that, well, the strain in the concrete is always going to be 0.003, but then we're also assuming that the strain in the steel, and the contention steel, epsilon S1 is 0.005. That is the boundary of the tension-controlled range. So first, let's show the strain. It's going to look very similar to some previous cases. I have my epsilon S1 and my FC here, or my epsilon C. So 0.003 and my 0.005, and that's going to be my epsilon S1 is 0.005. Then I have some sort of epsilon S2, and then I have my depth to my neutral axis C at some point that we'll have to find. So I need to find C first, and I do that by just, again, as always, applying similar triangles. 0.003. Compare this triangle to this triangle, big top one to big bottom one. 0.003 divided by C is equal to 0.005 divided by 13.5 minus C. And this then comes to a C equal to 5.0625 inches. 5.0625 inches. Now I need to find the, I need to apply another similar triangle in order to, just like I did previously, I need to apply another similar triangle to find epsilon S2. So epsilon S2, if I can write that properly, divided by 5.0, oh, come on, let me just do this over here. Epsilon S2 over 5.0625 minus 2.5, again, just similar triangles, minus 2.5, is equal to 0.003. 0.003 divided by 5.0625. And if you run through those similar triangles, you will find that epsilon S2 is equal to 0.00152. And then for stresses, I'm going to have just similar things as before. So I'll just go ahead and draw this. Because I do know that in the tension controlled case, I do know that I'm going to have, so this is stress, I do know that the tension steel must be at 60 KSI. Can't go above that. And then we have our certain depth A here, which we'll need to calculate. A here, 0.85 F prime C, and our FS2. The stress in our compression steel. So let's get those. A, I'm not going to bother calculating 0.85 F prime C. We've done that to death already. A is equal to 0.8, same thing as before, times 5.0625, again, just beta 1 times C, times 5.0625, and this comes to 4.05 inches. And FS2, the stress in the compression steel, is going to be equal to 0.00152 times E, or times 29,000 for steel, and that is going to equal 44 KSI, or just 44 KSI here. So next, I need to apply these stresses and create forces. So I have all the stresses of everything on my final point, and I need to create forces from this. So I need to create some forces from this here. And let's see. Let's double check something here. Yes. Okay. So now I'll get the stresses, or sorry, I'll get the forces. So I have FS2, capital FS2. I have CC, and I have FS1. FS1 is just going to be 60 times 4, 60 KSI, times the area 4 inches, or 240 kips. FS2, again, I'm going to put in a fudge factor to make sure I'm not double dipping between compression steel and compressive concrete, or just concrete. This is going to be 44, so basically I subtract the stress that's present in the Whitney stress block. 44 minus 4.25 times 4, and this then comes to 159.1 kips. And CC, the compressive force of the concrete, is going to be 0.85 times 5 times my depth of Whitney stress block of 4.05 inches. 4.05 times a width of 16 inches, and that comes to 275.4 kips. And all of this must come together to produce the Pn and the Mn, the nominal axial capacity and the nominal moment capacity. Now finally, let me apply equilibrium. Apply equilibrium. Well, Pn is going to be equal to 240 plus 275 here, and then minus the FS1, or sorry, FS2. So it's going to be, that is 240 plus 275 minus 240, or sorry, that's 240, let's see. Minus 240, yeah, sorry, wait, I got this a little backwards, sorry about that. 159.1 plus 275.4 minus 240. Yes, that looks better. 275.4 here minus 240. And that then comes to 195.6 kips. 195.6 kips, and then Mn is going to be here. Well, again, taking moments about the centroid, it will be 240 times 13.5 minus 8 plus 159.1. 159.1 times 8 minus 2.5. And then plus 275.4 times 8 minus 4.05 over 2. And that then will altogether come to a Mn equal to 3,841 kip inches, or 320 kip feet. 320 kip feet. And so the fifth point then is going to be 320, comma 195.6. So let's put this all in the graph for the first time. 195.6. So I'm going to first, I want to put all these things on the graph for the first time, and our graph will actually start to take shape. But immediately after we'll see a problem, and see we're not quite done yet. So let's see here. If I plot this out, my Pn, Mn, Mn and Pn, Mn and Pn. If I plot these points out, so let's see, first point 1 is going to be up here at 1534. Point 2 is going to be down here at negative 480. This is going to be in kips, and this is in kip feet. Mn in kip feet. And this is going to be down here at negative 480. So that's basically our point 1, our point 2. And of course, if you were doing this properly, you do this on graph paper would be the best. Then you're going to have a case here where, let's see, here, case 3 would be where you have 386, comma, what was that? 386, comma, 386, comma, 417. 386, comma, 417. And then points 4 and point 5. Point 4 is going to be here at 261, comma 400, comma 261, comma 957.4. Any objections to that? I think I got that right. Let's double check that. Yeah, 957.4, yep. And then down here at point 5, 5 here, and so this is 4. And then 5 is going to be 320, comma 195.6. And our overall curve, our envelope here, is going to be something crudely drawn like that. There, move the dot. Okay. If you can't nail the dot, move the dot. Okay. So this is our general curve. However, what is the problem with this? Any idea? We have a glaring problem with this, a glaring omission. This is nominal capacity. Can we actually design according to nominal capacity? No, we need to design according to the design capacity. We need to reduce these by some sort of factors here. So let me go down the phi factors. So here, let's see. Let's find this. Now, let's see. We now need to apply the code to calculate design capacities. Let's see here. Let's think about this. So note for tied columns, and this is a tied column rather than a spiral column. For tied columns, the code uses a phi equal to 0.80. And so Pn in each of these cases will equal, say, for example, for our first case, here, of 0.8 times P naught, P0, P0 times 1534. So we're not necessarily directly adjusting our, we have to make a little bit of adjustments here. This is going to equal then times 1534. This equals 1227 kips. So we're never going to be able to go more than 0.80 here. Because again, even in the case, if you remember from last time, even for tied columns, so here, actually, sorry, this wasn't the phi. The phi is not equal to 0.80. If you remember from last time, we apply a 0.80. 0.8 is multiplied by the nominal capacity before you even apply a phi. By the nominal capacity before phi is even applied for tied columns again. And this is basically saying, okay, look, even for the case where we're assuming there's no moment, we're still going to say, okay, well, there's going to be some moment there, so we're not going to allow ourselves to go over that. So I would just graph this as a line. This becomes a limiting line. I'm going to call this line 6 on our diagram. So we're going to trim this graph here and trim this at 1227 and say, you know what, even though the curve might predict up here, we're going to limit ourselves at line 6 at 1227. So I'm trimming the acceptable region. So the assuming pure axial capacity might say we're good above here, but you know what? I'm just going to say, okay, the code's never going to allow us to go over 0.8 times the axial capacity, even before we get to phis. So here, and then we have that. Okay. So then let's look at our phi factors. Basically, I'm going to go through each of these and calculate the appropriate phi factors. I have points 1, 2, 3, 4, 5, etc., and I'm just going to calculate them based upon that. So I have points 1 through 5. I'm going to go and calculate like point 1a, point 2a. Basically, 1 would be the original point, and 1a would be the phi factor, the reduced point. So let's also consider phi factors. So I need to remember for flexure that here, that I have this kind of thing going on. I have this kind of thing going on, where if I look at the strain in the steel versus the phi factor, you have this thing, 0.65. This is the phi, 0.65 and 0.9. And it has this kind of behavior, if you remember from our previous discussions. And so if you're in the tension-controlled region, it's going to be, if you're in a balanced region or the middle region here, it's going to be an interpolation. And then between there, it's going to be, so here, beyond the 0.005, it's going to be 0.9. Below 0.002, it's going to be 0.65 for our phi factor, and between them you interpolate. So let's go down the list and calculate the reduced capacities for each of these. So let's see here, 0.1. Well, this is going to be a tied compression controlled column. And so this means that phi is equal to 0.65. So that means I had 0.1, but now 1a, I'm going to put on the chart, is going to equal 0.65 times 1227, or equals 798 kips. 798 kips. 2.2, so that's going to be, and again, I'll have, this basically becomes the point 0,798. 0,798, 0.2. This is tension controlled. So here phi is going to be equal to 0.9. So phi is equal to 0.9. So phi PN then is equal to 0.9 times the 480. And this is going to equal 432 kips. So that becomes a point, this is 2a, 0.2a, of 0, 432. 0, 432. Any questions so far? Oh, sorry. Huh? Yes, actually, yes, thank you. That would be negative, yes. Negative 432. Next, I gotta get 0.3. So 0.3. Okay, so again, all we got was our compression and tension controlled cases. I do have to move through this kind of quickly. So negative 432. For 0.3, now I need to find where I'm going to be at. So here, epsilon S1 is epsilon Y in this case, which equals 0.00207. And so this is going to be, that means that our phi is in the transition region. In transition region. And if you go ahead and calculate that, you will find that the phi is equal to 0.656. So therefore, so we're going to multiply that by both P and M. So here, then 3a, so for 0.3a, if you multiply the previous values by our new phi factor, this is going to be here. Phi PN will come to 273.5, and phi MN will come to 253.2. And this is kip, and this is kip feet. So our ordered pair then will be 253.2, 273.5. And I might go a little bit beyond time today, but please bear with me. We do get out early sometimes. Okay. So we have that. Then on 4, I need to apply, I need to look at 0.4. Point 4 then. Let's see. Let's take a look at this here. And 0.4. So here our epsilon S1 is going to be less than 0.002. So phi is just going to be equal to 0.65. And so if we do our multiplications, if we multiply our previous capacities by 0.65, Pn is going to be 622, and phi Mn is going to be 170. So our 0.4, basically our 4a, is going to be here. This is going to be what? That's going to be, so let me double check something on this math. 1227 times, let's look at 0.65, and yes, that's 798. Good. Okay, I'll need to explain something further. 4a, so again, our ordered pair is going to be 170, comma 622. And 0.5 then. 0.5, for 0.5, this is in the tension-controlled region. In fact, it's the limit of that region, and we actually calculated everything, assuming epsilon steel 1 was equal to 0.005. So therefore, from our phi diagram previously, we see that phi here is equal to 0.9. So our phi Pn, well, let's go ahead and mix it up and do phi Mn first. Phi Mn is going to be equal to 0.9 times 320, and that's going to come to 288.1 kip feet. Kip feet, and then for the Pn, 0.9 times 480, 195.6, and this comes to 175.1 kips. And then the final thing we just need to adjust is factor line 6. So previously we calculated the reduced capacity, the reduced allowable capacity, just based on that 80% reduction factor. Basically, there's a thing in the code that says you can't have an axial capacity greater than 80% of the overall capacity. So we've already calculated that line, and now we need to factor it by a design factor, a phi factor, in order to calculate a design value for that line. So then line 6, so basically 5a here becomes 288.1, comma 175.1, and line 6, well, this was, so this is a compression controlled region because it is a pure column, definitely compression controlled. So here, the phi factor is going to be 0.65, and the value we had previously of P equal to 1227 kips times 0.65 is going to equal 798 kips. 798 kips. And, huh?
For the first value for 0.1.
The first value for 0.1.
Use the line 6 value or the original value?
For the original value for 0.1.
Yes. So for 0.1, use 1227 instead of
Let's see. Well, actually, that's going to come to the same. That's going to come to the same value, basically. Because basically, 0.1 doesn't actually appear on the graph anymore. It was trimmed by the line 6. Okay. So it's been merged with line 6, basically. So then the final version of this. Let's see. Do I have room to draw it over here? You know what? I probably do, actually. Let me go then and draw this maybe in a different color. Maybe a nice purple or something. So I have a reduced, then within this outer graph, I have my actual design capacities, 432. And let's say if I find all these points, so I have 5, and then 5A would be 288, comma, 175. That's 5A. 432 is 2A. Then I have a reduced value. Let's go ahead and get 3A here. 3A at 253, comma 274. 4A at 170, comma 622. And then, even though I could mention, I could say there's a point 5A up here, really what's going to happen is my curve is going to be clipped at 6A. So 6A here at 798 is 6A. And now I just have basically a limiting line here. So instead of having a point, we're limited to a maximum capacity, and the curve is going to go something kind of like this. And it'll go smoothly up to that point, and then it'll just be horizontally across. The axial capacity, just pure theory approach, would say that you could extend this further. We could extend it further, but the code says you're not allowed to use anything beyond this, beyond the 6A line here. And that really is our final capacity, our final column curve. Once we have this, we now know, and again, this would be much better if plotted on graph paper. This is something you really want to do on graph paper, but this is how you ultimately design concrete columns. Now, often you do this modified by or assisted by software, definitely, but this is the basic process, and there are a lot of pre-calculated ACI column design curves that you can use. So in terms of once you actually calculated this curve for your column, once you actually have this, the way you use this as a design tool is that you say, okay, well, once you have this, all you have to do is say, well, this is I do not have a single capacity anymore. I do not have a simple, dirt simple, oh, here's my moment capacity, here's my axial capacity, check each. They have to be checked together. And the way you do that is you say, okay, well, I demand that my column carry this axial load and this axial moment. You go up to your plot and say, okay, is that inside the factored curve or outside the factored curve? If it's inside the curve, you're good. If it's outside the curve, you're not. And that is the basic idea for calculating the capacity of short concrete columns that have moment and axial force interaction. Questions on any of this? Now this is quite a lot. I went through this fairly quickly, but I did want to do a nice long form example for calculating a full column interaction diagram. So there's that. If you have any questions, please let me know. That'll do it for today. Have a good Thanksgiving break, and as always, thank you.